I apologize for the quality of this. Usually I have a camera stand that I use, but I'm just going to hold my camera. Oh, I'm actually going over number 4. So in number 4, you're given the wind velocity. So I've just drawn the velocity vector here. It's 38 kilometers per hour, and it's at a 25-degree angle. It looks like this is eastward, so it's 25 degrees north of east. And I've just resolved this, or I've shown this is the y velocity, and this is the x component of the velocity. What I'm going to do is take some vectors, and then you can see my table down here where I've got x and y, and I've got 2 component vectors over here, and then the resultant vectors. So these components, the x components should add up to the resultant x, and then the y components should add up to the resultant y. At any rate, back to the component vectors. This is the wind velocity, and so the velocity of the wind relative to the ground. And then there's the helicopter airspeed, which is the velocity of the helicopter relative to the wind, or relative to the air. We don't know that. That's what we're looking for in this question. And then we're given the actual velocity. So this is the actual direction that the thing is traveling. Actually, we don't have the velocity, but it's pretty easy to come up with. So this angle is 17 degrees. If this is north, then the direction is 17 degrees to the west of north. And this would be the x component, and this would be the y component. Now, when you have an object, like the helicopter is the object, and it's moving through some medium, in this case the air or the wind, you can think as the medium, then the actual velocity of the helicopter, the actual movement of the helicopter relative, this is relative to the ground, or relative to the earth, that's always going to be the resultant. And you put the helicopter speed through the air and the air speed relative to the earth, put those two together, add them up, and that gives you the result. It's just like on a river, you've got the flow of the river, and then you've got the movement of the boat through the water, and those two things together combine to give you the actual path of the boat across the river. So this vector plus this vector gives me that. These are the two components, wind velocity and airspeed. This is the resultant. So I can take each of these vectors, the wind velocity vector, which is this arrow, and the helicopter airspeed, that's what I'm looking for, and then the resultant vector, which is that arrow, and I can resolve them into an x and y component of this, and an x and a y component of that, and then an x and a y component of that. Actually, I'm going to be looking for this. So for wind velocity, which I have right here, the x component is cosine of 25 degrees times 38. That'll give me Vx. So I wrote that there. That's what it comes out to. The y component is going to be sine of 25 degrees times 38. That gives me Vy, and that's 16.1. For the helicopter, I can't do that yet. I mean, the actual velocity, this one over here, I've skipped a step. I haven't really mentioned this yet. In the problem, we're not really given this 91 kilometers per hour, but we're told that the helicopter travels 182 kilometers in 2 hours. Therefore, it's actually going 91 kilometers per hour, so we can put that in there. So the Vx is going to be sine of 17 degrees times 91, and Vy is cosine of 17 degrees times 91. So there's the sine and cosine. Oh, notice how I have negative here? The reason that's negative is because this Vx is leftward and this Vy. So that's the only negative value here. This is up, this is to the right, this is to the left, this is up, so it's just that Vx. And I suppose if I put in negative 17 degrees and took the sine of that, it would work. I don't know. But I do know that this needs to be negative 26 degrees for the x velocity right there. Now that I have it, things are not, the hard part's over. All the x velocities, so the components, here's a component, there's a component, this is the resultant. So the x part of the first component vector plus the x part of the second component vector needs to equal the resultant. I've got this, and I've got that, and this plus whatever goes here needs to equal that. So this negative 61 I arrived at by saying if this plus this equals that, then this one equals negative 26.6 minus 34.4. So that's what I've written here, and that's how I arrived at negative 61. So now this plus that gives me that, as it should. And here again, I came up with 70.9 by subtracting 87 minus 16.1. So now these two components add up to the resultant. So these are the x and y parts of the helicopter velocity, airspeed, and direction. If I want an actual number, since I drew a tiny little diagram over here, if I want an actual number for that, I put in, I guess the diagram doesn't really help with that, but I can use Pythagorean Theorem. So vx squared plus vy squared, take the square root of it, that's going to be v. And I get 93.5 kilometers per hour. I'm squaring this, taking the square root. The direction, I want to find this angle right here. Now I know I've drawn my two vectors. Oh, sorry, just a second ago I said that wrong. It's not these things, it's these. These are the ones. This squared plus that squared, and then take the square root of that, and I get 93.5. So I've drawn a little picture of the resultant vector, and I've drawn that by taking the y component and drawing it 70.9, and the x component negative 61 this way. So I know this angle theta is going to be some angle above westward. If this is westward, then this angle is going to tell me how high above due west I am. And that angle, I can use tangent to come up with it. This vector I could also move over here. So I've got a right triangle with the opposite equal to 70.9 and the adjacent equal to negative 61. So I can do the inverse tangent of 70.9 over 61, and I get 49.3. And I just put in the absolute value of that. Works. So 49.3 degrees is the direction north of west there.